This is a tutorial on neutralization, the first aim being identify hazard symbols and define the term acid, neutral, base and alkali. Then can you explain how to perform neutralization reactions? And finally, explain how to test the effectiveness of different indigestion tablets. Now the term acid deals with a wide range of chemicals. Some are relatively harmless, like the acids we eat in fruit, whereas others can be quite harmful, such as the acids we use in a science labs, hydrochloric acid, sulfuric acid and nitric acid, to name a few. We also see in many sci-fi films that aliens spew out horrible toxic acid onto their victims to kill them. Our body contains a strong harmful acid in our stomach called hydrochloric acid. Now luckily I'm not talking from first-hand experience, but I've read that it's an incredibly painful place to be shot, the stomach, and that's because as well as the searing heat from the bullet penetrating your body, also the stomach acid will leak out and start to digest other organs. So it's a logical question, why is your stomach okay with it? Well, your stomach is lined with special cells called epithelial cells, which basically secrete an alkali mucus which neutralizes the stomach acid where it is in contact with the stomach lining. So acids can certainly be dangerous chemicals. So it's a pretty good time to introduce hazard symbols. Many chemicals in a school lab or in any sort of lab will have special symbols on them. These denote the kind of damage they can do. Now learning these is far more important for the foundation paper than the higher paper. But let's just zip through them. So the skull and crossbones means toxic, which means the chemical is poisonous and can kill you. I should probably mention that you have to consume or ingest a toxic chemical for it to kill you. An X with an H next to it means harmful, so the chemical can cause you harm but not necessarily kill you. An X with an I next to it means irritant, so for example the chemical could irritate your skin and cause you to itch and scratch. A flame with an O in the middle is an oxidizing agent. That means this chemical can chuck out a lot of oxygen, so you need to be careful when heating them, because oxygen can make fires raw. Obviously, a flame means the chemical is flammable, and acids and alkalis can also be corrosive. That's when they can eat away into your skin or flesh or metal. Some chemicals called indicators can tell us whether a chemical is acid or alkali, and some indicators can even tell us more specifically how strong the acid is, or how weak the acid is, or how strong the alkali is, or how weak it is. Universal indicator is a good example of such an indicator solution. Every acid and alkali can be given a pH value. pH values vary from 0 all the way up to 14. Universal indicator changes colour and lets you identify exactly what pH the chemical is. So, if a chemical has a pH of 0 all the way up to 6, it is an acid. 0 would be the strongest and 6 would be a very weak acid, such as acid rain. 0 would be something like hydrochloric acid or battery acid. If a chemical has a range between 8 and 14, then it's a base. A base is like the opposite of an acid, but that doesn't mean it's not harmful. Some alkalis or bases can be very, very harmful. The difference between a base and an alkali, a base is the solid form, and when you dissolve it in water, it forms an alkali. So the bases which dissolve in water to form a solution would form alkali solutions. Slap bang in the middle, we have neutral substances. These are neither acid nor alkali. The best example of a neutral substance would be water. So acids change indicators sort of red to yellow colour and vary between pH 0 to 6. Bases turn an indicator sort of blue to purple colour and vary between pH 8 to 14. Acids are generally chemicals which chuck out hydrogen ions, whereas alkalis are chemicals which chuck out hydroxide ions. Now when you react a hydrogen ion with hydroxide ion, HOH, you make the chemical H2O. 2 H's, one here, and the O here. H2O is water, and water is neutral. That's why when you react certain acids with certain bases or alkalis, you get a neutralization reaction because you produce a neutral substance. But be aware that it depends on which chemicals you're reacting. If you're reacting the ends of the spectrum, so this with this, then you will get a neutral substance. But if you were to react pH 14, for example, with pH 5 or 6, then you'll end up with something in the middle over here, which wouldn't be neutral, it'd still be alkali. So the acids and alkalis have to be of equal and opposite strength to fully bring about a neutralization reaction. So that is how we identify hazard symbols and define the term acid, neutral, base, and alkali. So now let's look at neutralization reactions in more detail. Here's the basic formula. If we add an acid with a base, we will produce a metal salt and water. Both these substances are neutral. That's why it's called a neutralization reaction. They both have a pH of 7. Metal salts, which can sometimes just be called a salt, just like table salt, which is a metal salt, sodium being the metal, sodium chloride being the metal salt, can be very useful to us. So when you react an acid and base, we get useful products called salts. Salts can be used to make fertilizer, fireworks, and plenty of food additives, including colorings as well as flavor enhancers. But to keep it simple, you only need to know 3 acids, those being hydrochloric acid, or like your stomach acid, HCl, sulfuric acid, H2SO4, or nitric acid, HNO3. You will need to know the chemical formula for these, especially if you're setting the higher paper. These are just things you have to learn, you can't work them out. But do be aware they all start off with a hydrogen, because I said acids chuck out hydrogen. The 3 bases you need to know are metal oxide, so any metal that has an oxygen attached to it, like sodium oxide, potassium oxide, so something which ends with O, metal hydroxides which end in OH, so sodium hydroxide for example, or metal carbonates like calcium carbonate, sodium carbonate, and they end with CO3. Now you'll notice here that I've shaded metal carbonates in a slightly different colour. That's because as well as producing metal salts and water, carbonates will also produce carbon dioxide. Hydroxides and oxides will only produce metal salts and water, so please remember that because they will test you on that. So know that metal carbonates will always also give you carbon dioxide. So most of these reactions you'll just need to remember the various products formed, but the one thing you can work out is the metal salt that's formed, and it's very, very easy. All you do is pay attention to the metal used in the reaction, so that would be zinc, it will always be the first chemical in the compound, or specifically in the base. And you listen to the sound of the acid, so here we've got hydrochloric acid. So the metal salt will be formed from the metal and that part of the acid, so we'll get zinc chloride because we're reacting zinc oxide with hydrochloric acid, so we'll get zinc chloride and obviously water. There's our metal salt, there's the water, both of them neutral. If, for example, we had magnesium oxide, then we'd get magnesium chloride, or copper oxide, copper chloride. Remember, you know this because of the sound of the acid, nothing else. Here's the balanced chemical equation for this reaction. There's a tutorial on balancing equations which you should watch if you're not sure how to do these. But I would like you to pay attention to the state symbols here. Remember, all acids are aqueous. Again, if you're not sure what this means, watch the balancing equation tutorial. All bases will be solids, and when you react them together, you'll most likely get a dissolved metal salt. Those are given an aqueous symbol because they're dissolved in solution. If you were to boil off the water to just leave the salt behind, then you'd see it in its solid state, but as it is dissolved in solution, we say aqueous. And of course, water will always be liquid. So now let's try another one. Sulfuric acid plus potassium hydroxide will produce potassium sulfate and water. Once again, listen to the sound of the acid. We've got the metal, potassium, and we're reacting it with sulfuric acid, so we make a sulfate. So potassium sulfate will be the metal salt. Of course, we'll also make water. Here's the chemical symbol equation again. So H2SO4 for sulfuric acid, KOH for potassium hydroxide, and potassium sulfate here, and water here. Again, look at the state symbols. You'll notice this time that I've written aqueous by this compound here. That means that the potassium hydroxide has been dissolved in water, so it's in solution here. That's why this is aqueous and it's an alkali, where this is a base because it hasn't been dissolved in water and it's solid. So once again, remember, sulfuric acid produces a metal sulfate. You just need to remember the name of the metal, which will be in the reactants with the alkali or the base, and the sound of the acid, sulfuric acid. So now let's look at the final example. We have nitric acid and we're reacting it with copper carbonate. And once again, we're getting the metal salt. This time it's copper nitrate, water, but because it's a carbonate, we also get carbon dioxide. Once again, listen to the sound of the acid. So we have nitric acid and we're reacting with copper carbonate. So the salt will be copper nitrate. You can pay attention to the state symbols again, but remember this time carbon dioxide is a gas that will bubble out. So remember, hydrochloric acid will always give you a metal chloride, chloric acid, chloride. Sulfuric acid will always give you a metal sulfate, sulfuric sulfate. And nitric acid will always give you a metal nitrate, nitric nitrate. Remember that all bases or alkalis, when reacting with acids, will produce a metal salt and water. Metal salt water, metal salt water. Carbonates will also give you carbon dioxide. So that is how you perform neutralization reactions. Let's look at how we investigate the effectiveness of different indigestion tablets. So let's first understand a couple of things about stomach acid. Stomach acid has two uses in the body. Firstly, to digest food, obviously, and then kill pathogens as well. You see, in a lot of the food we eat, we have a lot of bacteria on them, and our stomach acid does a good job destroying a lot of that bacteria, which can lead to food poisoning. So indigestion is a problem we often face when we eat way too quickly, and that stimulates our stomach to produce too much stomach acid. So indigestion occurs when we produce excess stomach acid, so much that it starts to burn at the bottom of your esophagus as it sloshes around, and that causes the sensation of heartburn. It's not actually your heart that's burning, it's your esophagus or the base of the esophagus, which doesn't have that special lining of cells that protects it from the acid. Indigestion tablets contain bases which neutralize excess stomach acid. It's really important that you understand it's just the excess stomach acid that's neutralized. So let's say we ate a meal too quickly and our stomach produces extra stomach acid. So this is the excess amount that must be neutralized. Of course, it would be awful if all our stomach acid was neutralized and turned into water, because we wouldn't be able to digest anything. It'd just be a bag of water in our stomach. So here's the method of how you test the effectiveness of different indigestion tablets. The first step is to dissolve one tablet in a fixed volume of water in a conical flask. So you can see here, I've got a tablet, I'm putting it in pestle mortar and grinding it into a powder. I'm then adding it to some water in a conical flask, a fixed volume, let's say 25 mils, and I'm dissolving it. The next step is to add a few drops of indicator to this solution in here. That will change its color. Obviously, it will indicate an alkali, because we know that indigestion tablets contain bases, and when bases dissolve in water, they form alkalis. You can see this green solution here. Green in this case does not mean neutral. It's because of the indicator I'm using that it's green. This specific indicator turns green when it detects an alkali. So next we fill a burette with hydrochloric acid. So a burette is basically this long plastic tube with markings which tell you how much volume of acid you've put in, and it's got a tap at the bottom which you allow to open and close to allow the acid to drip through. Next you will add the acid from the burette into the indigestion tablet solution drop by drop, and you regularly swirl it around to mix the acid within the solution. You can see me doing that here, drop by drop, and as it falls in, you'll notice the color change. You'll see suddenly it changes color, and I have to swirl it around to mix it in, and as I swirl it around, it changes back. What you have to do then is stop when all the indicator changes color, so the solution is fully neutralized.
So you keep adding the acid drop by drop until the solution completely turns color. This indicates that the solution has now been neutralized.
Then finally, you read the burette to find the volume of acid neutralized. In other words, how much acid did that single indigestion tablet neutralize? So you can see it's still swirling around, and now I'm going to read off the burette and record the volume of acid. The most important thing to note here is the most effective tablets will neutralize a greater volume of acid. That makes sense, it just tells you that that indigestion tablet is the strongest. Remember to control a few things in this experiment. Make sure you're using one recommended dose on the back of a packet. So it might say 2 tablets is an effective dose on one packet, but 1 tablet is an effective dose on another packet. Also make sure you are using the same amount of water to dissolve the dose in. Otherwise you'll be changing the concentration of the alkali solution. Make sure you add the same number of drops of indicator every time you test a tablet. Make sure you have plenty of hydrochloric acid in the burette so you don't run out. Make sure that you're adding the acid drop by drop and regularly swirling it. This is to make sure that you know the exact point at which the acid neutralized the alkali solution. And that is how you test the effectiveness of different indigestion tablets.